Hey, welcome to Info 3370, studying social inequality with data science at Cornell. Today we're talking about a really important topic for science, and that topic is reproducibility. Before getting into reproducibility, I want to background this topic with some of the conversations that have been happening in recent years about the credibility of social science and science more generally. So by the end of class, I'd hope that you'll understand reproducibility as an essential floor for the credibility of science. We're going to talk about some ways that you could go even above the floor to make science even more credible, but at a very baseline level, all results should be able to be recreated when given the same code and the same input data. We're also going to learn how to use RMarkdown to create reproducible documents. So let's get into it. This is a paper from 2011 published in the Journal of Personality and Social Psychology. That's one of the top journals in the field of psychology. And in this paper, Daryl Bem, an emeritus professor now at Cornell, argued for the presence of precognition. In particular, Bem evaluated participants to see their response to a stimulus. And the response was recorded at time 1. But the stimulus did not come until a future time, at time 2. And the studies showed, with statistical evidence, that people were able to precognate events that were going to happen to them in the future. So if this sounds like science fiction to you, that's because it's a little science fiction-y. In fact, it's really hard to believe that this precognition would happen. And yet, Bem seemed to follow lots of the standard procedures of science. There were participants enrolled in a study with statistical tests, and like all the quantitative evidence that you would think would ordinarily make for a successful article that might appear in the Journal of Personality and Social Psychology. And thus, the journal had no choice but to publish this paper, because it seemed in line with the standards of science. So if you step back and think about what this makes you feel about the credibility of science in this particular setting, you might react as many did to the publication of this article, by thinking, well, Daryl Bem proved that extrasensory perception is real. And what does that mean? That means that science is broken. And so when we think about this study, we have to ask ourselves, how is it that a study could follow all the standard scientific procedures, but produce a result that none of us would be able to believe? So moving forward, that particular study led to a whole flood of new studies that sought to replicate psychological experiments. In particular, researchers went out and tried to create the same stimulus and the same conditions as in the original studies to see if they could get the same result. So this is one paper published in Nature Human Behavior, where the authors replicated 21 major psychology studies and found that often they had trouble replicating the results. In this New York Times column, Andrew Gelman writes that the experiments are fascinating, but no one can repeat them. So repeatability is really a key criterion for the credibility of experimental evidence. In particular, in psychology, we might say that the ability to replicate a study with new participants is central to the credibility of that study. And this would be true in any setting where we might make a hypothesis and then collect data to evaluate that hypothesis. You would hope that if you made the same hypothesis again and then collected data, you could again get the same results in favor or against that hypothesis. So now I want to step back and think about how should we think about replication in other settings beyond experimental places where we're collecting new data to evaluate a hypothesis. This 2x2 table comes from Fries and Peterson's Annual Review of Sociology paper about reproducibility in science. And something I like about this table is that it highlights how there are various ways you could imagine recreating a scientific result in a new context. So in the top left of this chart, we have verifiability. That's what happens when you take the old data that were used to make the old claim, and then you apply similar procedures to those data. And you would hope that when you take the old data and similar procedures, you would come to the same result as in the original study. That's like a baseline requirement for believing the study was credible. So now if we go to the bottom row of this table, we have a similar setting and similar procedures, but applied to new data. So that's like what happens when a psychologist replicates an existing experiment by running the experiment again and collecting new data on new participants in some new experimental setting. Now, if we move from the left column to the right column, we're moving from evaluating a study in a similar context to where it was initially carried out to evaluating it in a different context. So if you use the old data, but you apply different procedures, then you can see how much the study is robust to the application of different methods than those used by the original author. And we might hope that our results don't totally hinge on the methodological choices that we've made, so that if you take the old data and you do slightly different things to it, you might hope that that result would be robust to those changes. And then in the bottom right corner, we have sort of the most extreme kind of generalization, which is when we take an old concept and we change it a little bit. We do something a little different, and we apply those different methods to new data. And if science is working really well, we might hope that we could succeed in generalization, where you could take one finding and then move it to a slightly new context, slightly new methods, new data, and see if that finding holds up. All four cells are something we might strive for in science. But the bare minimum, the thing we really absolutely have to have, is verifiability in the top left. If you have a result and then you apply similar procedures to the same data that were used to create that result, you would really have to hope that the result would hold up under those circumstances. So this is a bare minimum for us. And yet, it's hard to meet that bare minimum. So this is an essay published in Science that argues that artificial intelligence faces a reproducibility crisis. And by reproducibility, we just mean that if you take the same algorithm and reproduce the results, say on a new machine, then will you get the same result again? And it turns out that often the performance of an algorithm depends on things like the versions of the software and like where it starts in a random number generator. And when our results depend on things like that, it should make us uncomfortable. In this paper by Pong and Eckel, they describe all the processes that go from measured data to the output that appears in a journal article. And in many ways, this illustrates what we might hope for if we're striving for a goal of reproducibility. We might hope that it's transparent how the measured data become the analytic data. So responses on a survey become a database that's available in our computer to analyze. Then we'd like transparency as we move from the analytic data to the computational results. What models were applied? How did we subset the analytic data? Then moving from the computational results to the reported results, we'd like to have code that takes those computational results and produces all the figures, tables, and numerical results that are going to be reported in the scientific output. And then finally, it should be transparent how those figures, tables, and results appear in the article itself. So as the author, we should really strive for having transparency on all the steps, moving from the left of this figure over to the right of this figure. When we're the reader, we experience the article in the opposite direction. So we might first read the article and then dig a little deeper to see how the figures, tables, and numerical results support the argument of that article. Then we might dig a little deeper to see how the author took computational results to produce those figures, tables, and numbers. And then we might go even further back to see the steps the authors took in their code to move from the analytic data out to the computational results. So this figure is great because it shows how you really want transparency all the way from the measured data over to the conclusions that are claimed in the text of the paper. This figure is also great because it shows how the author can think about this in a forward direction and the reader can think about this in a backward direction. So what does it look like to strive for reproducibility at this level? I want to talk briefly about this paper by Liu and Salganik, which was part of a larger collaboration that I and many others were part of. In our project, we invited hundreds of people to build predictive algorithms. And a few of those people came together to write up a summary of their algorithm for submission to a special issue of a journal. And in that special issue, we asked all of the authors to submit not only the text of their paper, but also all of the code that produced their results. So David Liu and Matthew Salganik took this to like a new level. They decided to rerun all of that code and see whether when they ran the code, they got the same results as the original authors of the paper. So I'm showing you here what they found. On the left side, we have results when they compare the predictions from the algorithm as provided by the author to the predictions on the y-axis that they arrived at when they reran the code provided by the author to produce the predictions again. And you can see in this particular example on the left side, those predictions are not always the same. And that should be concerning to us, because that was the same code that the author used to produce the predictions, now used by a new set of people to produce the predictions. And we should worry that those are not the same. When Liu and Salganik dug into this some more, they discovered that the package versions of the R packages used in this analysis were not the same in the original analysis and in the replication. So then in the right column, they show the results once they aligned the package versions from the two. And here you see perfect alignment on that 45-degree line, where the predictions generated by the author exactly equaled the predictions created under the replication. And this is what we should strive for in reproducibility, that we should be able to hand our data and our code to someone else and have them produce not approximately, but exactly the same result as we produced initially. So in this class, and in general, I would argue that every result you create should be reproducible. And in this class, that's part of the evaluation criteria for every assignment. For this goal of reproducibility, the software that we're going to use is RMarkdown. And RMarkdown is super helpful on this front. So just to tell you a little bit more about RMarkdown, I would encourage you to read carefully chapter 27 of the R for Data Science textbook that we've been using, which is going to tell you all about the basics of RMarkdown and how it embeds code in the file and how that code can produce results that are very transparent where they came from. In addition, I'll highlight that there is this RMarkdown cheat sheet, which you can search for and find on the RStudio webpage. And it tells you lots of the key commands and things like how to format your code in your RMarkdown file to produce the output that you want. So I would recommend that cheat sheet as a good resource that perhaps you should bookmark when you're using it. And then I want to quickly show you what it looks like to actually use RMarkdown so that we can walk through this together. So here I've got my RStudio window open, just as we've always been using our RStudio window. So here at the top left, you might be used to clicking over here to get a new file. But if you click the little black arrow, then you can click down here to create a new RMarkdown. And right away it pops up a box that asks you some questions. So I'm going to title this document Example RMarkdown File. And see, it has the author, and here it has the date. And then you can choose HTML, PDF, or Word output. So let's start with HTML output, and in a minute we'll move on to PDF output. So once I start that, you see now I have a file ready to go. So let me save this file on my computer. RMarkdown example, let's call it. Okay, great. So at the top of the file, you see some information in the header. So this header here has the title of the file, the author, the date, and the output type. In this case, it's going to make an HTML document. Then there's some setup code here that you can just generally leave there. This is going to be put there for you by RMarkdown. Okay, and then below we can see an example of an RMarkdown document. So a few things to note is that there are headers, there's text, and there's chunks of code also. So before we do anything, let's go ahead and knit this file. So knit is the word that means we're going to take the code in the RMarkdown file and convert it into a summary document. So let's click knit here, and in your console you can see that it's now rendering the file, so it gives you little updates about how it's doing. And then in a second it'll pop up with a window showing the results. So we can see here this is an HTML file, and we have the title and header info up here. Here you can see how these two hashtags indicate a header, and when you have more hashtags, it's a lower level header, and fewer hashtags, it's a higher level header, so bigger. So here the header RMarkdown got translated to here. Then this text here gets translated over here as text, and you see you can format things. So here knit is bold, and that was created by putting 2 asterisks on either side of the word knit. And again, all these things are covered in the textbook chapter and also in that RMarkdown cheat sheet file. A code chunk here is where we embed our R code. So here it's going to summarize the data frame cars. And you see over here we have summary cars. And then when it knits this file, it runs that code and puts the output right here. So here the cars data frame has two variables, speed and dist. And down here we have a plot, and you see how it embeds plots automatically like this. So what does this look like if we wanted to use our Markdown for a data set that we have studied in class? So here I might type something like, we are going our Markdown to study median incomes in the US. And then maybe I want to have a header here that says code. And now I'm going to put my first code chunk. So to put a code chunk, you have 3 backticks. That's that character that on my keyboard is in the top left button. And then you tell it this code chunk is going to be R. And we end the code chunk with another 3 backticks here. And perhaps what we're going to do is study median income. And I'm going to pull that data set from the course website. There I have it twice because I had copied the whole thing. Okay, so just as in R, I can hit Command or Control Return, and it'll run that code. Okay, and it says could not find function read CSV. So what happens when I can't find the function? That's because I didn't load a package. So let's add up here a section for loading packages. And let's make sure we load tidyverse as we always do. Okay, so we load tidyverse. And then we load the median income file. Okay, and as before, remember what's in median income is this is a data frame with years and incomes, and this is the median household income in the US in each of those years, standardized to $2022. And so now, as before, we could summarize the data frame using an R chunk. So that would work 3 backticks, R, and we might do summary median income. And now if we knit, our Markdown is going to go all the way to the top of the file to an empty environment. It's going to load the tidyverse, it's going to load the data set, and then it's going to summarize that data set. And you see all the output appears here. So this is an advantage of R Markdown, where while you're working with R, you might have some things in your environment up in the top right, and it's not always clear when you generated those things or how they were generated in the code. But when you create an R Markdown file, every time you knit, your code runs all the way from the top to the bottom. So it's totally transparent how every piece of the results was generated. Okay, 2 more things I want to highlight for you. So one is that you can type math in R Markdown. So for instance, if I was going to run a regression model, I might do a couple $signs here. 2 $signs on each side will make a centered mathematical equation. And I might say perhaps the expected value of y given x equals alpha plus x beta. And you see RStudio will give you a little preview here of what you've typed. And when I knit, that math is now going to appear in my R Markdown output. And there it is. Expected value of y given x equals alpha plus x beta. So R Markdown is great because you can have your code, and you can also use it as a super helpful editor for presenting things like math. And then finally, like I discussed before, you can have headers, you can have things in italic or bold, and you can do lots of formatting things like that. And finally, you can also use inline R code to generate a particular number. So for instance, if I wanted to put the range of years captured in this data set, I might say these data contain the years And now I could hard code 1968 to 2022. But now what if something changed and I modified the data set? Then this would not get updated from that modification to the data set. So it would be slightly better here to put this directly in by having code that looks at the data set and gets the range of years in the data set. So in this case, we might have the minimum median income dollars year to the maximum median income dollars year. And so here, this chunk is going to say, use R to find the value of this thing, use R to find the value of this thing. So I'm going to knit here. And again, it takes a second because it has to run all the code from top to bottom again. And so we see here that you can have headers. This is the pound sign with the headers. You can have things in italic with 1 asterisk or bold with 2 asterisks. And you can say things like these data contain the years minimum year to maximum year. And that gets translated as 1968 to 2022. So you see how this is great for reproducibility because you have your document and you have the code file that produced that document. Now the final thing I want to discuss is that so far we've been knitting to an HTML file. And when you do a problem set, we want you to knit to a PDF file. This might require extra tools for having a small version of LaTeX on your computer. And there's help in the Ed discussion board about how to make sure that's set up on your computer. And if you're not part of the class and not on Ed, you can just Google how to work LaTeX for RMarkdown, and it'll give you tips on how to get enough LaTeX installed on your system so that you can make a PDF. And once you do that, you can click this down arrow and then click Knit to PDF. And you see it's changed my output to PDF document up here. And now it's doing its knitting. And there we are. So now we have the same result, but it's in a PDF file. So we have our code chunks with their gray background, and we have the same kind of results here. So a PDF here works just like an HTML, and you just need a tiny bit of extra software to make that happen. So that's it for our introduction to RMarkdown. In class, in groups, we took our code and interpretations from Monday and put them in an RMarkdown file and then posted them as a PDF on Ed, just to practice doing this a little bit. So I'd like to close by retouching on the learning goals from today. I hope that from this class you've understood reproducibility as really an essential floor for the credibility of science. If you're going to make a claim using data, then I hope that you can produce that claim in a reproducible way where you could hand your inputs and your code to someone else and have them produce that same claim again. And then second, we've touched on using RMarkdown to create reproducible documents. So I'll stop there, and I'm looking forward to our next class, which is going to involve survey samples of individuals.